Hello student to the Foundation of Classical Electrodynamics course. So, today we will going to start our module 2 which is electrostatic, and today we will going to discuss about the concept of charge, charge density, and if time permits then Coulomb's law. Class number 20, not 20, 21. Okay. So, our topic today we start electrostatic. Okay. So, the first thing that we are going to discuss about charge. So, we know that we have two kind of charge available in the nature. One is negative and another is positive, and these they interact with themselves with certain amount of force, like charge they repel each other, unlike charge they attract each other. So, force between two charges are, this force is a one of the fundamental force is nature. This is one of the fundamental force. So, that means there are other force also available. So, if I list them, so which are the fundamental force? The fundamental forces are namely the gravitational force, where we know that the force is defined by two particle m1 and m2, which is the mass, and if r is the distance between them, then this is the way it works. Then the second one is strong force. This is a strong nuclear force I am talking about, which is a short range force. So, it is range is around 10 to the power minus 15 meter, typical range of the short range force is around this, where I mean this is the force where you know that if you have a nucleus and inside the nucleus these are suppose protons, they are staying in a very tight region, even though they are all with positive charges, but they stay there. These are protons and they stay there because of this strong force, nuclear force, and basically they binds the baryons and muons. Okay. But this is a very short range. I mean this range you can see it is around 10 to the power 15. So, that is why it is a short range force. Another kind of nuclear force is also available. This is called the weak force. this mediates the neutrino interaction. And finally, we have the electromagnetic force. Okay. So, these 2 3 written in the blue color are the strong and weak force, but these are the short range force. On the other hand, this gravity and magnetic force, they are the long range force. So, this electromagnetic force, I mean this is a Coulomb, essentially this is a Coulomb Lorentz force. So, if I write down the force, it is Q E plus V cross B. The first part is Coulomb force and second part is Lorentz force due to the magnetic field, and that is why it is called the Coulomb Lorentz force. Coulomb Lorentz force. So, this is the form of this force. Well, if I want to find a qualitative understanding about the range, about the the magnitude of this strong force and these things, if I consider this strong force to be 1, suppose the magnitude, then the ratio if I take, then the electromagnetic force should be the 1/100th of this strong force. So, EM force divided by strong force is of the order of 10 to the power say minus 2. So, 2 order less. On the other hand, if I we will calculate that maybe the gravitational force, and if I compare the electromagnetic force. So, this value, if I make a ratio of the gravitational force divided by electromagnetic force, it should be of the order of 10 to the power minus 39. So, gravitational force compared to the electromagnetic force is very weak, that we need to understand. Now, at this point maybe we can discuss about the why we call this topic as classical foundation of classical electrodynamics. So, in electrodynamics classical theory, and classical theory, whatever the theory we are going to discuss in this entire course, this works wonderfully well for say macroscopic macroscopic distributions. What are the macroscopic distribution? Like capacitor, then this kind of system like electromagnet, capacitor, etc., where we are not dealing with a microscopic element. So, in this regime the classical theory works nicely, but it became very difficult to work in this classical domain when the scale is microscopic. So, when microscopic so difficulties arises at the microscopic level when quantum effects begin to assert. That means, when we try to understand this standard electromagnetic theory, which we call the classical theory, in microscopic level, when the particles or charged particles are microscopic in nature, then the quantum effects will going to arise, and this classical theory does not work well there. Now, what is in quantum level? What happened in quantum level? If I try to understand very crudely, then in quantum theory, in quantum electrodynamics, what happened? So, the charged particle interacts with each other. Here what happened? The charged particle interact with each other by exchanging say some exchange of force carrier which is generally called the boson. So, that means constantly when two particles are there in quantum level, these two particles, they are going to interact with themselves by exchanging, continuous exchange of force carrier. In the form of bosons. So, now for another thing we need to, so this is one thing, and another thing is, if I try to understand this very crudely, this is a very crude statement we are making, just to try to understand that what happens in quantum level. So, these carriers, whatever the carriers I mentioned, for long range force, are massless. And this is eventually these massless things are nothing but massless bosons are nothing but photon. And what is long range force? Long range force I already mentioned here, the gravity and electromagnetic force, these are the long range force. So, you can see that for electromagnetic force, when we have the electromagnetic force, then in quantum level the two charge they are interacting with each other by exchanging particle, and this particle should be massless in nature, and we called it photon. Okay. Later we will maybe going to discuss this in detail. Okay. So, you can see that this is one aspect. The next very important aspects that we need to understand at this point is something called action. So, these two particles are, these two charged particles are there, suppose, and the inverse square law, whatever the force we are having here, which is proportional to 1 by say r square, this works very nicely unless these two charged particles are static, okay, at rest. But if one charged particle moves from here to here, then the question is, how does the force between, if this moves, the question is, how does the force between them, whatever the force they have, instantly change? So, the meaning is, suppose this particle, charged particle sitting here, and a very long distance another particle 2 is sitting. Now, okay, they have the interaction with this force, the inverse square law. So, they know each other, they are interacting each other with that force. Now, suddenly one particle is moving from this point to this point. So, what happened, that how instantly the force will change here, because how this particle will know that this particle 2 is changing from this point to this point, because we know that it will take some time the information to go from this point to this point. This is the basic understanding of the special theory of relativity, where it is considered that no information can move faster than light. So, obviously, if they are very long, they are very long distance, so there should be some time it should take to go the information go from this particle to this particle, and the information is it is now moving in another point. So, that is, but here we consider that they are changing instantly, and in physics it is called action at a distance. So, that means as soon as the particle change from this point to this point, this particle will going to know instantly that there is a change, and accordingly the force will going to change there. So, so this action at distance is saying that if I say, if the source charge moves the long range nature of the force requires that the force may change instantly. Instantly. So, there is an instantaneous change of this force, and that assumption is called action as a distance. But as I mentioned that the special theory of relativity does not consider this. If you consider the special theory of relativity, this concept is no longer valid. So, what we get from this brief discussion is the classical electrodynamics this thing does not take account one, quantum mechanics, and two, special theory of relativity. So, this is not classical electrodynamics, the subject we will going to discuss here in this level. It does not take account the quantum mechanics and special theory of relativity at all. So, all the charged particle there stand still, static, and this static charge give rise to electric field, static electric field, and when it moves, it is moving with a constant velocity, that gives rise to this magnetic field, and when they accelerate, they will radiate, the electromagnetic radiation will be there. But at this stage, we will consider this is action at a distance, and purely the classical picture we will going to discuss, where the quantum mechanical aspect, that means in the micron, in the microscopic level what happens, or what happened if the charge is moving relatively, these things will not going to take account. So, that is why this course is in classical level. Also based on that, we like to mention one thing. So, suppose we have one charge here, say big Q, and I am putting a test charge very far away. So, this is say small q test. Now, obviously, by putting this test charge here, it should have some field with itself. So, there should be some change in the force between them. So, we will consider that this is infinitesimally small. So, when we calculate the electric field, this electric field should be calculated under the limit that this test charge is vanishingly small, and whatever the force we are having, this is force divided by that test charge. So, for unit amount of test charge, what will be the force we are having, that we consider as electric field here, and with the limit this tends to 0, and this is the way we define the electric field now on, that I just have a very tiny amount of charge here, which is having vanishingly small amount, and then whatever the electric field we have, and mathematically this is the way we define to get rid of the interaction of this charge which is present here. Okay, with this very brief discussion about and a overall discussion about what happened for classical picture, now we go back to our initial discussion, which is charge. So, the charge has few properties, and now I am going to discuss that. So, one is conservation of charge. So, conservation of charge means the total charge in isolated system never change. So, whatever the total charge we have, so the total charge in an isolated system never changes. Whatever the charge is there, it should remain. Second important thing is the quantization of charge. So, whatever the charge we are talking about, this charge is quantized, and the unit charge is nothing but the charge of the electron, and this value is around 1.6 into 10 to the power of minus 90 coulomb. So, the minimum charge one can have is this, you can't break it. So, whatever the charge, total charge we have, that is some multiple of this charge E, where E is a positive integer, the integer. Okay, that ensures that there is a quantization of charge. Next thing is the interaction. So, the interaction I already discussed, but since we are making it in a pointwise manner, so let me do that. So, the next thing is, so interaction among the charge. So, interaction among the charge is like that, the same charge, say plus or minus, they will repel, and like charge, unlike charge, that plus and plus, they will attract each other. Okay. So, like charge repel and unlike charge attract. What is next? The next is how to define the volume charge. Suppose we are having a arbitrary volume here, and inside that we have a tiny volume element. Okay. So, this is a chunk of charge, and we have this volume. Okay. So, the volume charge density the volume charge density is defined as rho, that should be a function of r. Now, for this tiny region, if I have dq amount of charge, then dq should be equal to rho r, this is a volume charge density, over this volume dV. Okay. So, if I want to find out what is the total charge, then the total charge will be the volume integral of this quantity charge density dV. We are going to use this expression several times. After that, very important thing, that is the classical point charge. So, classical point charge are vanishingly small charge that carries a finite amount of charge. So, these are the scattered classical point charges. And suppose this charge is Qk, this is the kth charge, k is integer, it is 1, 2, 3, 4, 5, 6, etc. Now, the charge, if I want to find out the charge density of this, what is the charge density? Of these discrete point charges. Now, they are not a continuous, like before this is a continuous charge distribution here, but here this is scattered, this is discrete. So, there are, suppose there are n charge particles are there, total number is n, and all the charge particles is having, so this charge particle q and its position is say r k with certain coordinate system here, right. So, this is the coordinate system, and in this coordinate system these charges are distributed with different location, and this is discretely distributed. So, I try to find out what is the charge, what is the density, charge density. So, charge density for this case, which we defined earlier with rho, can be represented as this. K can goes to 1 for n number of charges what we have, and each charge associated with a delta function r minus r k. So, each point at delta function, each r point we have a charge, and if you make a sum over that, then eventually we will going to get rho. Now, it looks quite I mean it is not quite straightforward, but we can find it quickly. How will you find it? Let us see. So, our total charge q should be the integration of rho r dV. This is the way we do the integration. We find that the total charge can be defined in this way. Now, I know the charge distribution, charge density. I just defined the charge density. So, I will put it here over the volume integral. So, this q r I put this value. So, this is summation of k equal to 1 to n. So, this I am putting, and then I put q k, and then I put delta of r minus r k, and then dV. Okay. So, I just put this, and then I put dV. Let us put dV in the different color. dV. Okay. So, now I can do in this way. The next step, I can take this out, because q k is nothing to do with dk, this is discrete charge amount. So, it is simply summation over q k, k goes to 1 to n, and then integration of delta r minus r k dV over volume. Now, this is a well known information, well known term, that if I integrate the delta function over entire volume, I should get 1. So, this thing is nothing but summation of k equal to 1 to n all the charges, which is nothing but my total charge q. Okay. So, this is the way you can define. Okay. So, now quickly try to understand what happened for the moving charge, yeah, what happened for the moving charge. So, next thing quickly we discuss about the moving charge, concept of the moving charge. Moving charge. So, this leads to the concept of electric current. Electric current. So, now suppose I have a surface here and the charges are flowing like this, and so this is the way the charges are flowing. And this is the region, I just take this small region. So, ds, if I want to find out the area here, ds, this should be ds n unit vector, n is along this direction, n unit vector, and this is the flowing current density. I should put J because charges are flowing here, and this is the total surface S, and this surface is ds. Okay. So, J here which is a function of r and t is called the current density. Crudely saying, the amount of current passing through per unit area. So, di, the amount of current in terms of current density, is simply J dot ds or J dot n ds. The total current I is the total charge divided by time dq dt, and that should be equal to the integration of this di, which is integration of J dot ds. Okay. So, now this if I have a closed surface, for closed surface, I can have this integration, closed integration. So, J dot ds, suppose the surface is closed, I have a volume kind of thing, then this quantity is eventually the divergence of J. By using the divergence theorem, I can write it. This is my equation, say 1. Okay. So, now if I have a volume, and if this is the volume I am having, suppose, and total charge are flowing out, and I am taking the closed surface, this is the J flowing out, J flowing out. So, the total charge Q should decrease in the volume, whatever the volume we have. So, Q should decrease. So, the current also I can write here that since it is decreasing, so it should be minus of d dt, and the charge density we know if it is decreasing. So, I can write it in this way. So, this is simply minus of del rho del t and dV. This is equation 2. So, if I compare equation 1 and equation 2, from equation 1 and 2, I find a very interesting relation, that is the divergence of the current density, over a volume dV is equal to minus of this quantity del rho del t over dV. So, from this equation I can compare and find that del rho del t is equal to 0. This is a very important equation in electrodynamics, also in quantum mechanics you will have this equation. It is called the continuity equation. So, this continuity equation will be very important, because it basically tells us when the current is flowing outside. So, that should be equivalent to the divergence of that should be equivalent to the rate of change of the divergence of the current density is equal to the negative of the rate of change of the charge density. So, that is why this quantity is called the continuity. So, in order to maintain the continuity of the charge flow, we need to have this equation. So, later we will going to discuss about this equation also when we deal with Maxwell's equation, but at the beginning it is better to have a note that how charge flow give rise to the current density, and then if I try to understand in terms of the charge density, then what is the relationship between the current density and charge density. So, this is a constant relation between the charge density and current density, which we call the continuity equation. So, with this note I would like to conclude here. Thank you for your attention. See you in the next class.